Hey everyone, thanks for having me. So today I want to talk a little bit about some of my lab's work on value alignment for AI systems and some of the ways that I think that relates to social intelligence. Um, so first, what do I mean by alignment? So one definition that's a sort of very broad umbrella definition of the value alignment problem that I happen to like is the following: that highly autonomous AI systems should be designed so that their goals and their behaviors can be assured to align with human values throughout their operation. And this definition I just like because it sort of contains two different parts. It contains sort of from a reinforcement learning perspective, we think about behaviors being aligned as, sort of the policy being aligned with what people want. Meaning that, the agent actually does the thing we want in the end. But then there are also goals that, we care about, that the agent is sort of trying to optimize the correct thing as well, meaning that the reward function is aligned. And of course, there's also the problem of whose values, which is its whole own sort of social problem that is very important, but outside the scope of what I'm going to talk about today. So for the purpose of today's talk, just think that, we're in a very simplistic scenario where we're trying to learn about like one person or one group's sort of values. So, why do people work on value alignment? One of the sort of most common reasons is just practicality and deployability. So, if we're going to put robots into people's homes and workplaces, no one's going to want to use these if they don't actually do the right thing, right? People will lose trust in them very fast. Stepping up one degree of severity, we have safety and sort of social harm issues as well. So, there's been a lot of talk about this with large language models. But, as, more and more self-driving cars are sort of, being sort of tested and used on the road, we've seen, deaths and other injuries increase as well. And finally, there are people who are concerned with existential risks of sort of, more serious catastrophic sorts of risks that can come from unaligned AI systems. So how's all this related to social intelligence? Well, I think on one hand, social intelligence is sort of just one type of alignment problem. We want robots and other agents to perform particular tasks correctly, but part of what correct means in most situations is acting in a socially intelligent way when the robot or other agent is interacting with humans. And part of the practicality and deployability, for example, is a robot acting in a socially intelligent, appropriate way around people. Part of safety and social harm prevention is understanding what human values are and sort of how to respect those in ways that don't cause social harms, and also a sort of higher level understanding of all the different things that are important to people that prevent an agent from perhaps hacking a reward function, which we'll talk about a little bit more later, in a way that's going to sort of do in a very exact sense what was asked of it based on the reward function, but in spirit do something that's very bad from a safety perspective. And of course, a more severe version of this is just existential risk. So I think that social intelligence is a sort of alignment problem in and of itself, but that also social intelligence is really necessary to solve the more general alignment problem in the first place. That without social intelligence, we can't really understand what human values are and correct ways to behave, because we're never going to be able to write down sort of every little bit of a specification for any particular task we do. Okay, but why is this hard? So, the reason I'm going to sort of focus on today that value alignment, that makes value alignment really hard, is just how easy it is to misspecify reward functions whenever you are trying to specify a task to, for example, a reinforcement learning agent. And this is because, even for just a simple single task, it's often just really difficult to sort of capture and balance, complex preferences and trade-offs in a single scalar reward. And you might say, well, this is something that, maybe only is hard for lay people, but not hard for reinforcement learning experts, for example. But there are so many edge cases that you might not think of, side effects that a certain reward specification can have, and these lead to reward hacking. And we showed in a recent paper actually that even when you ask RL experts, I'm talking about like PhD students, postdocs, professors, to write down a reward function for an extremely simple task. We were actually a bit shocked at how many really profoundly bad mistakes people make that lead to unwanted behaviors in the tasks that we defined. So this is not something that's easy in general. And you might say, okay, well, then we can just sidestep defining reward exactly and give demonstrations, for example. But this has its whole own set of challenges of collecting demonstrations of a certain form, and as well as sort of ill-posed inference problems that are really challenging as well. However, even if we are able to write down a really great reward function for a task, then there are also difficulties with learning policies in the first place. And this can come all the way from how we decide to define our problem in the first place, state action representation, for example. It can be difficult just because RL doesn't work very well in general. We don't have great RL algorithms yet. They can sort of perform arbitrarily poorly, or you might learn a good policy and then you have distribution shift. And even if you manage to learn a good policy at the end of the day, you might not want to deploy it unless you feel fairly confident that it's going to perform well in your final task. And so you want to be able to verify. But verification is also really difficult. Exhaustive testing is typically not possible. And there's often a lack of ground truth data to even compare against in the first place. So every step of sort of learning and deploying policies, is difficult. I'm going to focus mainly today, though, on the reward specification step, but all of these steps are extremely important. And I think actually social intelligence is sort of important in all of these steps as well. Okay, so the core question we'll be looking at then is, how can we develop reward functions that lead to socially intelligent robot behavior? So I'm going to talk a little bit first about just some sort of existing work that's out there right now on learning reward functions or inferring reward functions from people's preferences. And this is sort of an increasing popular way of doing reward inference that sidesteps a lot of the really tricky problems of learning from optimal demonstrations, for example, with like inverse reinforcement learning. But I'm going to talk about how virtually all the preference-based learning methods out there are sort of making a very particular assumption about what human preferences mean. And that if we sort of get this wrong about what human preferences mean, we're going to be making wrong inferences, and we're going to be aligning or misaligning, to the wrong thing. And finally, I then want to sort of talk about, bring it all back to social intelligence and think that, if we do want to use these types of methods to train socially intelligent agents, we're going to need data that is sort of scalable and natural for people to give. And so how do we really get that kind of sort of multimodal, naturalistic social feedback from people so that we can train these sorts of agents? Okay, so learning from preferences. Learning reward functions from preferences, or it's sometimes called RLHF, reinforcement learning from human feedback, is an increasingly popular way of inferring reward functions from people's preferences that they have, and then using them to either train policies or better align by fine-tuning policies. The sort of most well-known version of this is this paper in the upper left-hand corner, training language models to follow instructions with human feedback, which was the Instruct GPT paper, the sort of predecessor to ChatGPT. But lots of different approaches now are using this that sort of ranges from like active learning methods for robotics to alignment verification methods. It's being used all over the place. And the core of what's really being done is that you tell someone, what the task is in general, or they have a task that's sort of, already in their head that they want the agent to do. And then you just show a person, two examples of, trajectories or trajectory snippets or outcomes. And you just say, which of these do you prefer? And so, if the task is something, a really simple grid world where you just want the agent to get to the goal, and you ask, which of these do you prefer? You would imagine most people would say the one on the right, where the agent is actually going toward the goal instead of away from it. And what you then try to do is, given some model that you believe is the sort of generating process that, given a reward function, would cause the preferences to be generated, what you're going to try to do is then optimize some reward function to maximize the likelihood of having seen that preference data set that you saw. And so, of course, the missing piece of this is what's the model of preference? And the sort of most common model of preference that's used typically takes the form of like a softmax looking function like this, where you have some score function f that is telling you how good any given trajectory sigma is. And if you're comparing two trajectories, sigma 1 and sigma 2, the probability that someone's going to give you a preference of sigma 1 over sigma 2 kind of increases, the probability of that increases exponentially as sigma 1 starts looking better and better under score function f than sigma 2. And you can rewrite this as just a logistic function. So, of course, the key question then is, well, what are you using for f? What's your score function? And the current dominant model that's used in virtually all those papers that I just showed is the partial return. In other words, the sum of rewards in the trajectory snippet sigma, which seems reasonable. The more reward a snippet gets, it seems that people would prefer that more and more over a snippet or a trajectory with less reward in it. So this is exactly what was done, for example, in that Instruct GPT paper I mentioned. So what they did as one part of the paper was, for many different prompts, they collected pairs of outputs, stochastic outputs from GPT-3. Then they asked people, which of these do you prefer? They used those preferences to infer a reward function, like I just mentioned. And then they took that reward function and performed reinforcement learning on top of it to fine-tune the model. In a different example that's more in a robotics context, some work that my group did a few years ago was this model called T-Rex, where we took preferences, or you can really think about it as a ranking over agent behaviors. In this case, in this domain, half cheetah, where none of the behaviors are particularly good, but you can see the behaviors at the right are better than the ones on the left. And what we do is try to learn a reward function that explains what's making the better behaviors better, and then see if we can learn something that actually goes beyond the best demonstration in the data set. And you can see on the right, we're able to learn like this coherent run, for example, that's better than the best demonstration in the ranked set. So, these are just two quick examples of this sort of large and growing field. Like I mentioned, there are tons of other papers out there doing it, but the key bit is that all of these are really assuming partial return as the underlying model that is generating people's preferences, that's driving people's preferences. And we thought it was pertinent to ask, what if the partial return model is wrong? That seems like it would be somewhat disastrous, because then we're going to infer the wrong things about reward functions. We may overestimate how aligned a particular model is, etc. So if we really want to be able to do alignment through preference-based learning, we actually have to understand, what are reasonable models of how people generate preferences? What do preferences mean? So what's a hint that partial return might be a bad model of people's preferences? Well, if we take a look even at this like really simple grid world environment, imagine that the person has a really simple reward function in their head, where they just want the agent to get to the goal as fast as possible. So, one reward function that would do that is just -1 at every time step, right? And so the agent will just want to finish as fast as possible. So if you show someone with that reward function in their head, these two trajectories, the one on the left is 2 time steps long, it doesn't get to the goal, -2 total. The one on the right, same thing, -2 total. A partial return model should be indifferent to these, which feels wrong. It feels like the one on the right is clearly making better decisions, and most people will prefer that. In a slightly more complicated example, you could imagine on the left, you have a car that starts in a safe state where it's not going to hit a brick wall. And then it makes some really bad decisions, and it drives such that by the end of the trajectory, it's in a state where it is about to hit the brick wall, but it doesn't. And so there's zero total reward it gets for that trajectory. But there's another starting state on the right-hand side where it starts in a state where a crash is very likely, but it takes a really good action, maybe the best possible action even, and it manages to avoid the brick wall, but it kind of clips it a little bit. And because of that, it knocks the mirror off the car or something, and it gets a -1 reward for that. But it ends in a safe state. It made really good decisions. Again, partial return, because it got more total reward on the left, it's going to prefer the left segment. And that just feels wrong compared to how we sort of assume people really give preferences. And we confirmed this in some experiments. So what we're proposing is a different model of what we think preferences mean, which is based on what we call regret. And regret can really just be thought of as the quality of the decisions that are being made, rather than just the raw short-term reward that's gained in the trajectory or the trajectory segment. And the nice thing about regret is, when we think about quality of decisions, that's really a sort of inherently long-term quantity. And so the way of mathematically formalizing this is based on the optimal advantage function A star, which essentially models the difference between how good your action is and how good the best action is. And so the best advantage you can have at any given state is 0. And if we look at the regret-based model, intuitively, it seems to have some of the right properties. We're going to now prefer the trajectory on the right because it is making good decisions. It's going toward the goal. And so the Q values of those actions, or the advantage associated with them, are going to be better than on the left. And again, for this car example, it's once again going to prefer the trajectory on the right because better decisions were made. It turns out, though, that it's not just intuitively that this sort of seems to make more sense. The regret model actually has sort of nicer theoretical properties as well. So it turns out that the partial return model has a serious identifiability problem in that there can be two different MDPs that have different optimal policies, in fact. And the partial return model essentially cannot tell them apart, even with infinite preferences. It cannot see any difference between them. So on the left here, we have an MDP where there's only episodes are only one time step long. You take a single action, and you can take one of two actions. You can take a safe action, which is that route on top, and with 100% chance, you're going to get 0 reward. Or you can take a risky action on the bottom, and then there's a 50-50 chance you're either going to get -10 or +11. So that's the better action to take because it has a positive expected value, right? On the right-hand side, though, it's the same MDP, except now you have a 50-50 chance between -10 and +9. And so now you have a negative expected value on that branch, and it's better to take the safe action. But it turns out that the partial return model cannot tell the difference between these, because think about seeing each of these 3 possible trajectories that end in either the safe state, the lose state, or the win state infinitely many times, right? On both the left and right, you're going to have the same ranking between those, right? The win state is always the best, the safe state is always in the middle, and the lose state is always the worst, right? In both of those. And so anything that's based on partial return is not going to be able to differentiate these two MDPs. But it turns out that the regret-based model can, because again, it's thinking about the quality of actions. And the quality of actions has to do with the expected value associated with taking those actions. And so it can reason about these expectations, and it can actually take these apart, tell these apart. And it turns out that just in general, we were able to prove that reward is not generally identifiable with noiseless preferences from partial return, but it is from a regret-based model. Okay, so that's nice, but how usable is this model? Well, it turns out that it is computationally a little bit more, actually significantly more complex to use, because it requires computing Q star and V star for sort of reward functions that we're proposing during inference. So in this paper, we sort of assumed linear reward functions and use successor feature representations to do this efficiently. We're currently working on a way that we think we figured out to do inference without any of these sort of complications. So if you're interested in that, sort of keep a lookout in the next few months for that. But we don't think it's a fundamental problem. Okay, so this is all interesting, but like, is this actually how people give preferences? And so to figure that out, we performed a human study in this sort of simple delivery domain where a little bus is supposed to take a delivery to a particular spot in the grid. And there are things like, obstacles that, you lose points for hitting, coins that you gain points for picking up, etc. And we tell people sort of what the cost or the reward for each of these features is. We generate 100 of these different MDPs, and we showed them to a bunch of Turk workers where we got preferences over short trajectories that we showed them, where we allowed them to either say they like the trajectory on the left, the right, or they're the same, or they can't tell. And what we found is this graph, which is a little bit hard to interpret, but I'll try to walk you through it. So each data point, each colored point dot here is essentially two trajectories that, and the color represents the proportion of people that prefer trajectory 1 versus the proportion of people that prefer trajectory 2. So red being preferring trajectory 1, blue being preferring trajectory 2. The y-axis can be thought of as the difference in partial return between the trajectories. And the upward diagonal axis can be thought of as the difference in regret between the trajectories. The x-axis isn't as important. The x-axis is essentially the difference in quality between the start state and the end state of the trajectories. So if you look at the line, the horizontal line, y equals 0, that is the line along which there's no return difference at all between the two trajectories. And if people were giving return-based preferences, what we would expect is that we would just see sort of like a 50-50 preference. So we would see like all pink. But you can see we kind of have like the whole spectrum along there. And so it seems like return is not what's driving people's preferences. But on the other hand, that downward diagonal line is the line where regret is equal. And we do see that we have roughly 50-50 preferences along there. And if you look orthogonal to that line, we actually see a lot of variation orthogonal to that line, indicating that it does seem like people are giving regret-based preferences. And we confirmed this sort of numerically as well, that just from sort of a regression perspective, the regret model fits the preference data we saw better than a partial return model or a uniform random model. And we also showed that even though none of these are, even though the regret model is not a perfect model of how people are giving preferences, we can actually use different user interfaces to push people toward one type of preference or another. So we had one interface where we don't show them any additional information, one where we show them information that's sort of related to return, and another interface that's sort of related to regret, essentially. And we were able to show that when we showed them the return-based UI, return actually better explained their preferences than regret. And when we showed them the regret-based UI, regret won as before, and it won even more strongly than when we just showed them no information at all. So we don't just have to be able to sort of rely on perfectly modeling people's ways of giving preferences. We can also use priming techniques, essentially, to sort of push them toward certain interpretations, which is nice. Okay, so to summarize that section of the talk, we want to be able to learn from people's preferences. It's a really nice way of being able to understand what people want over time, without them having to like provide optimal demonstrations of what they want or anything like that. And we can use that to learn about what they want in tasks, how they want a robot to behave socially, etc. But if we really want socially intelligent robots, for example, it's important to be able to collect data at scale, be able to collect data over time in sort of an online iterative fashion, and really be able to collect data not just from these sort of artificial preferences of like, hey, like here's two options. Do you like this one better or this one better? But really collect it in the moment, in the social situation, that's going to put people, sort of in the moment and make them the most present and able to give really high quality feedback. And so one type of feedback that we've been looking at in order to do this is to collect what we call implicit human feedback. And this is feedback that rather than being explicit of saying like, do you like A or B better, just occurs naturally, isn't necessarily intended by the person to influence behavior of the agent, but just kind of naturally happens and can be collected and utilized without any additional burden on the user. And so one example of this is facial reactions. If you just watch, people's faces as a robot or another agent does things in the world, you can get a pretty good sense sometimes of how people feel about the various things that an agent does. So we have an algorithm called empathic that does this, and facial reactions were the specific data type we looked at in the paper. And it kind of works in two phases. In the first phase, we do sort of a data collection and calibration phase where we try to learn what people's facial reactions mean. So what we do is we tell them, hey, you're going to watch an agent perform a really simple task. And, every time it picks up a blue square, for example, you get, 50 cents. And every time it picks up a red square, you get $1. And every time it picks up a yellow square, you lose $1. So we assign different like positive and negative money amounts to this so that they're really invested in what they're doing. And we learn how to interpret their facial reactions, which are different, for everybody. And this is really hard because people lose attention. There are temporal delays in how they react. There are paradoxical reactions. People, often laugh and smile when things go really wrong. So this is, not an easy thing to learn. But what we showed is that, once we do this, across a lot of people, we can learn these models where we can actually learn an entire task from scratch from just facial reactions alone. So in natural language, we just described to the person how this sort of object sorting and recycling task was supposed to work. But we didn't give the robot any information about the task at all. The robot just starts out without any reward function and takes completely random actions and just learns from the person's sort of facial responses and body language if it's doing the right thing or the wrong thing at any given time. And it's actually able to learn the task completely from scratch just from that signal. Now, you could, of course, use this method in combination with a given reward function. We just wanted to sort of show the power of it, though. And of course, this is definitely not the only kind of naturalistic feedback that you can imagine getting. I think, it's there are so many different sources of social feedback humans use when they learn from each other. And, we eventually want to sort of expand to that entire range of things as well. And so we've looked at things like natural language, both task descriptions and corrections, like stay further away from the green block. We've recently been looking at audio and prosody data. So if someone's, watching the robot do something, or maybe they're even giving a demonstration, they say like, ugh, that's not natural language per se, but it tells you that something went wrong. And like, if it's a demonstration, you probably shouldn't mimic, what just happened there. If it's, just feedback, the robot probably did something wrong. And if someone does say something in natural language, like, don't do that, there's a real difference between them saying, don't do that, or don't do that, and don't do that, right? The second one maybe gives you a sharper notion temporally about what they're referring to. And it also gives you a sort of increased sense of magnitude. And so we've been trying to use all those cues together in order to better align agents and endow them with social intelligence. So in summary, how are we going to learn develop reward functions that lead to socially intelligent behavior? We really can't define them by hand. I think using preferences and other types of naturalistic feedback is a great way to go about doing this. And I think that it's not just a great way of aligning agents to be more socially intelligent, but really using social intelligence to better solve the alignment problem itself. Talked about these sort of two different interpretations of human preferences. It's really important that we figure out what preferences really mean. And I think this is just scratching the surface. Psychology, behavioral economics, they know tons about this, and it's much, much deeper than just return versus regret. But I feel like maybe this is at least the high order bit that we've started to tackle. And finally, yeah, we need to look at these sort of broader types of cues in order to really get scalable and rich data for doing this sort of thing. So the main paper I talked about today is here, if you want to check it out. And yeah, I'm happy to take any questions. Thanks.
If anyone in person has questions, you can raise your hand and come up to the podium. Oh, okay. Go ahead.
Thanks for the great talk, Professor. I have, I guess, one quick question or more general question about how you collect data from humans about their preferences. I mean, I guess there's always some inherent bias, right? Let's say in the example that you gave, where you look at the people's reactions. I mean, they might be biased in some way to have a more reactive phase than what they usually have, and things like that. So, did you ever consider taking, like, for example, YouTube videos to use the data instead of explicitly collecting the data from user studies? Thank you.
Yeah, so when we were collecting data, in the consent form, like they knew video was being collected, but we didn't specifically tell them that like their facial reactions were being watched or anything like that. And so we tried to make it sort of as naturalistic as possible in that sense, so that they weren't sort of, overacting or anything like that. But, as in all human experiments, I mean, everything from the way you phrase the task to how you, set up everything, ends up changing how people behave. And so I think sort of figuring out what the really optimal way of doing that is, I think is still a fairly open question.
Got it. Thank you.
I think we have time for one more question if someone in person has one. Going once, going twice. Okay, I think that's it for in-person questions.
Okay, I have a question. Thanks, Scott, for the amazing talk. So you have mentioned several times about like the human feedback, and it seems like very amazing. Like Instruct GPT, it has shown amazing results. So what's your opinion about the future of reinforcement learning with human feedback?
Yeah, so I mean, I think the hardest thing is that apparently, from what I've heard, it was very hard for OpenAI to actually get all that to work because you're just getting, in the most naive ways of doing this, a point estimate of a reward function from these preferences. And it's an underspecified problem. It's probably not a great reward function you've actually inferred. And if you train on it too long, you're going to get a really bad result. So they had to sort of limit how long they trained. They had to limit the KL divergence that was allowed from sort of the base policy that they had started with. They had to do a lot of things to get it to work. And so I think one of the future developments in RLHF is going to be figuring out how to get around that problem. And I think one possibility is if instead of inferring point estimates, you start inferring posterior distributions of reward functions, and then learning policies that are robust with respect to that distribution. I think that might go a long way toward solving that, but I think there's going to need to be more to it than that. But I think until that really gets figured out, there's just going to be really serious limits on how well RLHF can work. And there's going to need to be a lot of engineering in the background before it works. It's not just going to be sort of an automatic thing you can just toss on a robot.
Absolutely.